but we'll just see how things go. All right, chapter 17 is kind of fun, I think, but I have a weird sense of funness. So, I don't know. It's not awful.
You've been correct so far. Ice tables were
Yeah, there's ice tables in this, my friend. All right. This can get really confusing. Yes.
On my canvas, there's something that says AP Chemistry C, and then there's AP Chemistry 2020. You're still using AP Chemistry.
Yeah. The school automatically makes AP Chemistry A and B and C, and there are 3 different courses, but I just go with the one that I make myself because I'm cool like that. Okay, chapter 17, additional aspects of aqueous equilibria. This chapter has the content that is most likely to actually be on the AP test of any chapter so far. Well, chapter 4 is so broad that yes, it'll be on there, but like specific problems, this is very likely where they're coming from. All right, let's get after this. So here we go. You need to know what we call the common ion. The common ion effect, in fact. All right, so consider a solution of acetic acid. We have the acetic acid plus water goes to the H plus C2H3O2 minus, or the acetate ion. If acetate ion is added to the solution, Latlier says the equilibrium will shift to the left. Okay, so there's so much stuff here. Let me talk about what I'm talking about. We already actually talked about this at the very end of chapter 16. So I have this beaker. That's the one I want, but let's just erase it all. This is fun. Okay, we'll see how this goes. So I have my beaker. That's way too small. I don't know what that button is. I'm gonna fail in this. I'm off to a swimming start. Okay, we'll make a lot bigger beaker. There we go. All right, so we have HC2H3O2, and it's breaking up into H plus and C2H3O2 minus. Are we comfortable with that? All right, if I come along and add what we call a common ion, which would mean it's an ion that's similar, so C2H3O2. So I don't add like acetic acid, I add it as something that will dissociate. So I have NaC2H3O2, and I put it in there. It causes an increase in the amount of this, right? And so if the amount of acetate ion is increased, Le Chatelier's principle says I come back towards the acetate or acetic acid. Who's with me on that part so far? It what? It becomes less acidic, and we'll talk about why. Let me write this horizontally, and it might be a little bit better looking. So let's go here. So I'll write a little smaller. So I have H, C2H3O2, and then my double arrow, and it makes H plus C2H3O2 minus. So once again, what we're doing in here is by adding the sodium acetate. Okay, go away. By adding the sodium acetate, I add to this side, which means I really make the equilibrium go this way, correct? Okay, which means that I end up with less H plus. If I end up with less H plus, that means I have a higher pH. You okay with that? So I can affect, and once again, we said this right at the very end of chapter 16. I can affect the pH of a solution without adding an acid or a base if I add a common ion. If that ion abstracts or sticks to the H plus and bonds to it, then the amount of free floating H plus decreases, so we make it more basic. So far, so okay?
Is the NA just like a spectator? Doesn't
Yep,
do anything?
Na plus is just chilling here. It doesn't do anything because if you remember, hold on, is this even an option? Nope, I can't extend the page. But if you remember, Na plus is the conjugate acid of a strong base, so it stays completely a separate. It will have no effect on the pH.
And the acetate adds or drops the extra H plus.
Right, since it's the conjugate base of a weak acid. Okay, so the common ionic effect says that the extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. So let me write this out in words again. I'm just going to do HF because it's a lot easier to write. So if HF, we have H plus F minus. This is annoying. If we have these two things and I add to this solution, once again, like some sodium fluoride, I make more HF, correct? So it says the extent of ionization of a weak electrolyte, so that's the HF, is decreased by the addition of a strong electrolyte, that's the NaF in this situation, that has an ion in common with the weak electrolyte. So there is that and that. That is the common ion effect. Less of this breaks apart because we already have a high concentration of this. That shifts it towards the equilibrium. Fair enough. Yeah, and that's why we studied it a couple chapters ago, because it has a huge effect on everything we do in chapter 16 and 17. It's just called the common ion effect. I don't think it has its name. It's not named after someone. All right, I'm going to erase all this stuff. Oh, there's nothing to erase. It's already there. Okay. Are we good with this page, this slide? Okay, silence means whatever I want it to. All right, so here we go. Here's an example. Because HCl, a strong acid, is also present, the initial H plus is not 0, but rather 1 point whatever. So here I have a weak acid. All right, I have my water. It dissociates here, but in this table, I put some H plus. So it's just saying I already had, I'm adding HF to a solution that already has H plus. You okay with that? I think the next slide, let me make sure it's the same one. Okay, so it is the same one. So let's talk about what we're talking about in the previous slide. So if I have that H plus, but I drop in F minus, chemistry says F minus will find H plus, right? So if you think about this, let's see if there's an option. The concentration of H plus is going to decrease equal to the amount of F minus added. What's that? They can become equal, but this is more because HF is a weak acid, so it wants to bond. So if you already have, if you have a bunch of H pluses just chilling, oh, sometimes it reads my palm instead of my finger, but you have a bunch of H pluses in here hanging out. which means you would have a low pH, right? Or it'd be very acidic. And then I dump in, it doesn't have to be even HF, it could be NaF. I put that in there and this dissociates. You with me? It breaks apart into one Na part and one F part. Every F will find every H plus it can to form HF. So the concentration of H plus will decrease equal to the amount of F minus that we have present. Yeah, it can neutralize it. So we don't even add an acid, but we can neutralize this solution just by adding a salt with a common ion. Okay, it didn't even have to necessarily be a common ion here. It just needed to be something that could form a weak acid. All right, let's look at this problem real fast. Let me even read it here. All right, so this is a little bit different. I should have read this before I got here, but it's okay. Calculate the fluoride ion concentration. That's what it wants me to solve. And pH of a solution, that is 0.2 molar in HF and 0.1 in HCl. So this is tricky. We would think it would just be 1 because we have a strong acid and that means it completely dissociates. Correct? But it can't. Why? Because as soon as an H breaks off, it's going to be grabbed by an F. Okay, so here we go. I have an ice table here. I have my, what order do I even want to do this in? Okay, we're going to go with HF, F, whoops, H plus. That's just terrible. Tom Davidson. I almost had it. Okay, good. I hope that you don't mind this one. H plus and F minus. Why am I not making this for HCl? Because if it was for HCl, the initial and the equilibrium would be the same. But I have a weak acid. That's what I'm worried about. So what's my initial HF? It's 0.2. What's my initial H plus? Okay, it tells me it's 0.1. My initial F minus is 0, right? We okay with that? All right, then think about the following. Every H that is broken off will absorb an F. You sort of with me? So it will grab an F from here. So the amount of HF will decrease equal to the amount of strong acid I put into it. It's going to go down 0.1. Whoops. Okay, because HF will break apart, not much, but if there is another H out there, it will break apart to make more of it. The F will come off into the bond to make more. So that decreases. So at equilibrium, HF is what? 0.1. This decreases 0.1. This increases, whoops, sorry, this goes up 0.1. Are we okay with that? Or sorry, yeah, they're pluses. They're, no. Say that again. Yes. It breaks apart and then it grabs an H immediately. Yes. So I'm doing something wrong here. Oh golly, hold on.
There's a reaction point, we lost point one if that's the table script.
Yeah, we did. Hold on. I think, let me double check here. I definitely should have read here. Oh, I don't need this. What is this? Oh, well, this is not bueno, Tom. No, that's not true. It has been 2 years. This was not on the AP test last year because they shut down and they said, okay, we think you should have been to about X point in time. And it was chapter 14. They only tested 1 through 14 last year. So I haven't done this in 2 years. It's not that hard. I just don't know what I'm doing wrong. I don't remember. Oh boy, this is embarrassing.
You'll watch it. On my desk, yeah.
All right, I'm just gonna have to reread it because I don't remember what I'm doing wrong. I 100% remember these are not that bad. But that's not helpful right now. Oh, I know what I can do. Hold on. This isn't the first time I've ever forgotten what I'm teaching in this class, is it? Hey, supposed to say yes. Okay, I super have screwed this up. All right, I know what I did wrong now because I have it right here in front of me. And I tried to skip to the end of the chapter where we do buffers. Well, they're not the end, but I skipped like 3 slides and started to do math that actually isn't math yet. So, well, it's yes. Speaking of that, the last test, no, it was fine, but like, well, I took it out of 100 points, right? But if you did that test, it was like 7 questions. But the max you could miss on one was 5. So you got 65 points for free. I was grading this. I'm like, I am the biggest wuss grader of all time.
Oh, that's true. Like if you take off 3 points, it's like still a 97.
Right. Like you could fail it miserably and you got a 70. I'm not being mean. If you got a 70, send it. No one got a
Like the
70.
lowest score practical is 70.
It was a 65 is the lowest you could possibly get.
5 was the whole question wrong? 5 off?
Yeah, or 2 parts of one. If you didn't take the test, you got 100. Okay, ignore all this for a second.
Oh, if you like,
Yeah, if you were one of those,
yeah.
you're welcome. It should have brought everyone's grade up. Unless you had 100 before and you didn't get 100. All right, so here we go. Here is what I forgot.
Oh, so satisfying.
We'll see how it goes here. Oh, I'm not streaming it. So sorry. It's gonna disappear. It is Los Angeles for sure. Where are you? There. I can connect to the Fielding Elementary School's Apple TV from right here. Look right there.
You should give them a surprise.
I'm sure they have a code like I do.
You should link into it.
Okay, here we go. This is what I forgot, and I was being stupid. You'll see what I'm talking about. What I was trying to do here, you'll see what I mean in a bit. I apologize. So this is actually just like we've done before. There's just one tiny little sliver. So my initial was 0.2. That didn't change. My initial was 0.1 and my initial was 0. Well, why did it write it there? Did you see that? Like, I don't know why it went there. And that was 0. Okay. So now this is, and I apologize. This is a weak acid, right? How much of it dissociates? Ignore everything I said before. How much normally does it dissociate? A little bit. We don't know, so we call it X. We've done this before.
Oh, yeah.
Oh, you're going at the lines. I don't know what's going on either. Let me, yeah, I'll put my,
Get one of those artist things.
I have one of those, but I look so stupid in it. I have some pride, Judah. Let me see if I can find it. You look so stupid. I'm a straight up gamer when I wear that thing. What does what stand for? I don't know. Oh, that slides. I swear it's up here. I don't know where it is. I swear it's right in there. Here we go. Here we go. I'll get ready for the track meet right now. Oh, I got it.
Oh, yeah, this is actually kind of sad.
That's my middle name.
I said that. Okay. Whoa. Whoa.
Oh.
Oh, okay, dude.
Okay, guys. Okay. You guys are such weirdos. All right, then this is a minus, so this would be a plus, right? Plus X. You with me? Let me erase these stray things when I was too prideful to wear this awesome looking thing.
How can you be like that? It's like amazing. That should boost you.
Hi, guys.
That should boost you.
Yeah, my boost nothing. Okay, now this is different. Now it's 0.1 plus X, right?
You have to eliminate substitution.
No, I don't even know what that means. All right, and this is X, right? You with me?
Yeah. Sorry, I was thinking about the word.
It's okay. I have do not disturb on, but group me still, I don't know how to shut it off without going in and shutting it off, but whatever. I went to my settings. I've turned off all notifications. but apparently that doesn't turn off all notifications. Group Me is the cancer that we cannot get rid of in the school. Okay.
That'd be even worse.
All right, so here we go. 6.8 equal or times 10 to the negative 4. It's still catching. It's still catching. Equals 0.1 plus x times x over 0.2 minus x, right? Does this look like fun math? It's going to be ugly, right? Okay, so a long time ago, what did we say about this? We said that a weak acid, what was x equal to down here? It's almost 0, right? So why worry about it? You with me? So 6.8 times 10 to the negative 4 really equals these two things. The x would just disappear, right? You with me? And we'd end up with 0.1 x if we multiply across the top. Now, you might think, why can't the x on the right just disappear? Why can't this just be gone? Because then it would be a 0, and we'd have 0. And subtracting a small number doesn't really make a big difference, right? Multiplying by a small number makes a huge difference. So do you see that, why that one stays and the other one goes? All right, so do we need it in the denominator? Does this x need to stay? No. It's really small. 0.2 minus a really small number is really just 0.2. Okay, so then we just solve for x. You with me? So I multiply both sides by 0.2 and then divide that answer by 0.1, right? Anyone have me a number? Whoa, 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 whoa. Tolman, how about you? Okay, now. 136, okay. Okay, now is that an answer? That's this one, right? 0.00136. That's that answer. That is a correct answer. Okay, now what about pH? How do you find pH? pH, all right, it's equal to negative log of H plus, right? And we have H plus, we can calculate it right here. 0.1 plus X, so it's the negative log of 0.1, and then we add it 0.136, right? And did someone type that in? It's 1. All right. Can someone type in this? Negative log of 0.1. It's 1, right? So this is extra proof that really the x is pretty insignificant, because even when we did add it, come on. Even when we did add it, it made essentially no difference to the pH, right? Okay. Now, we point that out. Go ahead. Yeah, and it was probably like 1.00 something. What did your calculator say, Tolman? Yeah, so yes, for sure. But they're pretty much the same value. You all right with that? Okay, so what this was setting up, and it was dumb of me, is if I did, and we won't yet, but I have this, and then I add a common ion, we're going to see how that does drastically affect the pH. It's going to be called a buffer. So I apologize, I went straight to buffer math without actually doing this first. Okay, coming down here. So, well, it's just right there. So our pH ended up to be just 1. All right, so buffers. This is where you're the very most likely to get a question on the AP test. All right. Buffers are solutions that have a weak conjugate acid and base pair. They are particularly resistant to pH changes, even when strong acid or base is added. Buffers at first can have some pretty complicated math, but in the long run, they're really not. There's an equation we'll talk about pretty quickly that makes it so much easier. Yeah, that is rough. Does that make it clear? No, can't read it. I was trying to make the picture bigger so we could read what these actual buffers are. No, buffers are good. No, like if it has a low pH buffer, yeah, it would be. No, not at all. You drink soda pop, it's like a pH of 2. Yeah. That's like a -10. It lights my tongue up so fast. Yeah. Yeah. Yep, I would love to. I don't know where I was, but I go right there. Wow. But it's poisonous. It's a venomous poison. Let me know when I can move on. All right. Here we go. Okay. So this, we good over there? It's all right. So in this solution, it's kind of hard to see, but it's just a pain to erase. So let me change it to blue. Here we go. In this solution, we have HF and NaF that's just chilling. Okay, so I'll redraw it just down here. I have HF and I have Na plus and I have F minus. You okay with that? I want you to think about the chemistry that would happen if I come along here and if I were to dump in NaOH, I would now have Na plus and what else in here? OH minus. Wow. It did become more basic, but would there be any chemistry, secondary chemistry that would happen in this beaker? H plus is consumed. First, I'm going to get rid of these because they don't really matter, right? This is an acid, right? What do acids do to bases? They neutralize. So HF plus OH minus makes water and F minus. Are you okay with that? Okay, so in this solution, we have something that will react with any OH that is added, and that would be the HF. Are you sort of okay with that? Okay, so now let's talk about this. We'll put this in this nice, lovely burgundy color. All right, and we'll add to this solution some HCl. So we end up with Cl minus, which we're not going to care about, but also some H plus, right? Which should cause the pH to plummet, right? But is there anything in here that will react with the H plus? The F minus. The F minus will neutralize any acid that is added, and the HF will neutralize any base that is added. So if I have a solution that can neutralize both things, we call this a buffer. It works better, but still not perfect. I think it's because this program, the Smart Notebook program, is not, it's touch sensitive everywhere. But like if I were to use my notebook program that I use normally, it is not touch sensitive. It's only pencil sensitive. So it would work really well there, but it's not working very well here. I mean, it's still working better. Okay, so the idea of a buffer, it has something that can both neutralize an acid and neutralize a base. So the weak acid reacts with the base to produce water. The conjugate base accepts H plus to make a weak acid. We okay with that? Okay. This is probably just another drawing from another year. Okay. This is just going to say what we just did. So in this exact same example, if a small amount of hydroxide is added to an equimolar solution of HF and NaF, for example, the HF reacts with the OH to make F minus in water. So that's what I just said. So nothing new there. If acid is added, the F minus reacts to form HF and water. So there's something now, I call it the secondary reaction. It goes into water, it dissociates, but then it finds another pair to make a secondary reaction. The secondary reaction can both take up H pluses and take up OH minuses if they're added. That means it will maintain the same pH. All right, buffer calculations. We have 2 minutes. We're not going to get through one, so we'll pick that up tomorrow. This would be a great time to look in your textbook. I know you won't, but at least I said you should. Thank you. All right, kids, have a great day. If it starts raining hard, just think about me and Logan and pray for me. Yeah, this is the second day of the Cash Box Invitational. It's that Ridgeline. Yeah.